So I guess we are recording and sharing. So that's the best we could hope for under these circumstances. So hello to everyone, for people in class and the people in the virtual audience. And we continue discussing noise in metals. So I'll start with a few basic concepts that you probably all know, but worth reminding nevertheless. So I will start with briefly discussing a random process, which is a particularly important one, which is called Poisson process. So let me just give you a prototypical example of this process that you're all familiar with from the course of statistical physics. So imagine that we have an ideal gas placed in the container, and the volume of this container is with 0, and the number of particles of this gas is at 0. And then let us take a small fraction of this container with the volume of V, assuming that V is much smaller than V0. And ask, what is the probability to have a number n of particles to be within this volume V? Okay, so this is essentially equation, and these are classical particles. Let us think about classical particles. So this equation in the basic statistical physics or basic combinatorics, and the answer goes like that. So if you look at one molecule, then the probability to find one molecule in the volume V is just V over V0. So that's the number, which is the probability to find one molecule in this volume. Okay? So now, what is the probability to find n molecules in there? Well, obviously, this is the probability to find one molecule in the power n times the probability to find other molecules outside of this volume element times combinatorial factor n0 factorial n factorial n0 minus n factorial. So that's statistical physics 1. And if this is the probability, we call this probability binomial. So the distribution of a number of particles within the volume V is binomial. And then we'll take a particular limit. We'll take a limit, then V over V0 approaches 0, number of particles in the container approaches infinity, and the number, which is an average value of particles in the element V, approaches a constant. So this limit where binomial distribution W of n turns into what is called Poissonian distribution. So let me just briefly outline how it goes. It's roughly in this limit becomes n bar in the power n times n factorial 1 minus n average divided by n0 in the power n0, and this is roughly n bar in the power n e minus n bar divided by n factorial. And this distribution, it's called Poisson distribution. So it essentially describes a probability of having an event where there's extremely large number of attempts and 0, extremely small probability of success, and the product of these two quantities is finite. Now, what do we know about Poissonian distribution? Let us compute with this distribution. Let us compute an expectation of the square of number of particles in this volume. So this would be sum n runs from 1 to infinity, n in the power 2 wn. And this is equal e in the power minus n average. Sum over n runs from 1 to infinity, n average in the power n times n divided by n minus 1 factorial. And after we play with this formula, we get that this equal n average square plus n average. So which means that n square minus n averaged square, it's equal to n average, which was also denoted as a number. Okay. In other words, the second, there is a name for it. I think it's called a standard deviation, or second cumulant. And the second cumulant is actually equal to the mean value or first cumulant. And what you can show if you play with this thing, that for Poissonian processes, all cumulants are equal to the first one. Okay. So just to give you one more example of a Poissonian process, and this is the classical Poissonian process. It's known from electrical engineering. You have a device, a vacuum device, which you people probably never ever seen in your life, because you are too young. But once upon a time, there was such a device. It was called cathode. So it was a vacuum tube. And in this vacuum tube, you had a metallic plate here, and you have a metallic plate there. And you had and so it was really a tube. So here it was something approaching a vacuum state. Low pressure. Let's call it vacuum device. And how this thing actually worked. So you have a heater here that was heating this thing. So it has this thing got heated to a temperature T, and it was subject to the voltage difference between this metallic plate and another metallic plate. One of them was called cathode and another was called anode, and I never was able to remember. And now it's not needed because these devices no longer exist. But once upon a time, all computers were made of these devices. Yeah, that was the time when the size of the computer was like a building. Okay, so this is the vacuum tube, and the process. So if you zoom in onto this plate and the vacuum plate, so it was essentially a piece of metal with a very big, very big potential barrier that electrons need to overcome to get into the vacuum. So if electrons get into here, then it's a free propagation in the external electric field problem. So every electron that managed to get itself released from the metal will go and eventually hit the opposite end. But the escape problem from the metallic plate number 1 was a random process. So for each individual electron, there was essentially a huge potential barrier that electron need to overcome in order to get into the vacuum. And the electron has a temperature T and potential barrier, barrier was much larger than T. And so you can think about escape probability, which is minus U over T, which was very, very small. So these were events that each of them had a very small probability to happen. However, the plate was big and there were many electrons in it. So you can think about it as a random process where many independent events happened. Each one has a tiny probability to be successful, but since there are many events, you have a finite probability of success, and this will result in the current, which is DC current that was flowing through the anode. The number of electrons that managed to escape per unit of time. And then if you look at the fluctuation of this current in time, so you measure current, you have ampere meter, and you measure how this current fluctuates in time, and these fluctuations, the intensity of these fluctuations, if you Fourier them and take frequency to 0, were proportional to the charge of the electrons times the mean value of the current that flows through the system. So this is the second cumulant. This is the second cumulant. And this is the first cumulant. And this is because the process is Poissonian. So this is known for ages. So this is just a realization of a Poissonian process in a very basic engineering device. And what we learn from it, that the fluctuations of the current in this device are proportional to the mean value of the current. Okay, any questions so far? Okay, so this was just a reminder, quick reminder of what we all learned from the course of Engineering 1, Statistical Physics 1, and so on. And now let's take these ideas and apply for the Boltzmann-Langevin equation. So I remind you that last time we promoted our Boltzmann equation to become Boltzmann-Langevin equation. Here it is. This acts on delta F of P, R, and T. And this thing is equal to delta J external, let's call it external, of P, R, and T. And here I remind you, this object is a standard Boltzmann, Boltzmann operator. I would be a linearized collision integral. Function f of P, R, and T will now have a part which is average over fluctuations plus fluctuations. And this guy is a Langevin source. So this is something that reflects the fluctuation in the random processes that inevitably occur during collisions. So let us now zoom in and discuss how we understand those processes. That will be extremely important. So let us schematically draw the phase space, and let's consider a cell in the phase space that we call cell P, and another cell that we call P prime. And let's say that delta J of P, R, and T is a random flux of particles arising due to fluctuations into and out of the state PR. So there's this box at the point R. Let's say that this is the phase space at the point R. These are two cells that we are focusing on, P and P prime. One cell, that's another cell. And let us see what happens with these random fluxes. So let us consider a flux of particles that flows from the state PR into the state P prime and R. And we assume that collisions are local in space, so if electron scatters off something, say of random impurity, at the point R, it scatters at a given point. So it goes with the momentum P, it scatters, it acquires a different momentum, but everything happens locally at the point R in space. Okay, so let's denote this flux of electrons from state P to state P prime at point R at momentum T J. Similarly, there is an opposite flux. The opposite flux goes from state P prime into state P. And according to our notation, this should be labeled JP prime P and the point R at time T. Okay. Now, okay, so now imagine these two quantities, they are fluctuating in time. So sometimes the more current between these two from one state into another than on average. And the analog of vacuum tube is a perfectly legitimate one here. So we can, there was a direct current in real space between two parts of the vacuum tube, but here it's a current that flows between two places in the phase space. So then we can call delta J a fluctuation of this current and delta J is a fluctuation of that current, if we are discussing fluctuation. So let us discuss the net flux into the state P. So what is the net flux into the state P? Let's denote it as G, J, P, R, and T. This is how many excess particles are coming into the cell P at the point R at the time T. And this is obviously equal to the sum of all states in the system, delta J, P prime, P, R, and T, minus delta J, P, P prime, R, and T. And I can do a really non-trivial transformation and says that this is G of P prime, delta J of P prime, P, R, and T, minus sum of the P prime, delta J of P, P prime, R, and T. This guy I can call delta J plus P, R, and T, and this I can call delta J minus in PRNT. And this is fluctuation in the incoming flux, and this is outgoing. So the physical meaning is perfectly transparent, I guess, right? And now, since we're dealing with Boltzmann-Langevin equation, the statistics of fluctuation there will be determined by statistics of delta J of P, of the essentially of the statistics of this random flux. I'll show you later if it's not obvious right now, but it might be obvious that if we know this correlation function, we would know the correlation functions. From this, we will be able to figure out what is the fluctuation function of delta F, because the equation is linear. So if we know the correlation function of external noise, we will be able to find the correlation function of delta F. Okay, then to fully determine the equation, we need to establish the correlation function from Langevin noise. And I'm going to show you exactly how it's done. So let us write this thing as an expectation of value of delta J plus of P1, R1, C1 minus delta J minus P1, R1, C1 times delta J plus P2, R2, C2 minus delta J minus P2, R2, C2. And now let me open the brackets. Delta J plus P1, R1, C1, delta J plus P2, R2, C2, plus delta J minus P1, R1, C1, delta J minus P2, R2, C2, minus delta J plus P1, R1, C1, delta J minus P2, R2, C2, minus delta J minus P1, R1, C1, delta J plus P2, R2, C2. Okay. So we need to find the correlation function of these guys. And here we're coming finally to the main point of all this theory. So we need to tell the correlation function of an elementary, let's call it elementary scattering process, elementary scattering process. Consider a microscopic correlation function delta J between states, say P1 prime P1 at point R1 and T1, delta J P2 prime P2, R2 T2. So this is the correlation function in the random fluxes. So this guy is the random fluxes between state P1 prime to P1. This guy is a random flux between state P2 prime to P2. So this has two coordinates, the beginning and the end. This guy has two coordinates, the beginning of the end. So this is the random flux that of particles that start at the point P1 prime and end up at the point P1. And this is the random flux between these 2 points. So think about it as an analogy of a random Poissonian current in the vacuum tube. And now we need to postulate what this correlation function will look like, and everything will follow from this assumption. And the assumption is based on the picture that scattering occurs via many large number of uncorrelated events, and the probability of each event is very small, and the mean value of the total probability is finite because there's a large number of participants. So it's a typical assumption of all Poissonian processes. Okay, so let's try to guess what should be the correlation function of this object. So what is the simplest possible thing we can propose?
The Kane exponent?
So it's the function of, notice, 1, 2, 3, 4 variables. It's the function of 4 momentum, 2 coordinates, and 2 times.
A wave? No. So 2 deltas.
Okay, so deltas. So what deltas?
Position and time has to be the same.
Correct. So position must be the same because scattering here and scattering there happen independently.
Yeah.
Time also. What happened in the past has nothing to do with what will happen now. Absolutely no memory. Okay, so we got rid of that.
And P1 and P2 prime?
And delta P1 prime minus P2 prime. And delta P1 minus P2. So it means that only scattering processes that occur between same points in the phase space will be correlated. So I start from here and there. That's the only process that it's correlated. And finally, so these are delta functions. And finally, last but definitely not the least, so all delta functions been eaten. So all this is proportional to what? Think that, remember, this is a Poissonian process.
Number of electrons?
It's proportional to the mean current that flows from the state at the beginning to the state at the end. So this is the random flux between state P1 prime and P1, and its fluctuations are proportional to its mean value. Like the fluctuations of the current in the vacuum tube is proportional to the strength of the current that flows there. It's called shot noise. Once upon a time, it was called shot noise.
Not anymore?
I think, well, the name exists, but
the meaning is different?
Well, shot noise, I think, comes from the hunting. So if you hunt birds,
shooting will make the other birds go away.
No, the way to kill birds that you had, you didn't have a bullet, but instead you have many small metallic pieces in the gun.
Okay. Like a shotgun.
Yes, but I think that you write it differently. I think shot noise was coming from the shot noise of the smoke. And then people transfer it to vacuum tube for logic I don't really know, and vacuum tube do not exist either. So, right. But anyway, so it's a noise in the Poissonian process, and that's what it is. And this guy is an expectation value of the current that flows in the phase space between these two states. And we know that guys very well because that was a building block of our kinetic equation. You know what is the mean flux of particles between this state into another state. If you don't remember, that was the probability to have electron in the state P1 prime and to scatter to state P, and that was this. That was a familiar building block. This is how many electrons are being transferred from the state P1 prime into state P1 in the presence of some scattering. So this guy, it's already known. So, okay, so let's keep this thing on the back of our mind. So we discovered everything that we need to know. And now we can use this definition of the elementary random flux correlation function and plug it into the currents that we had before. For example, delta J P1 R1 T1, incoming flux delta J incoming flux in the state P2 R2 T2. This will be equal to the sum over P1 prime P2 prime delta J P1 prime P1 R1 T1 delta J P2 prime P2 R2 T2. Okay, so let's just plug it in. We know that this is delta P1 prime minus P2 prime, delta P1 minus P2, delta R1 minus R2, delta T1 minus T2, and mean value of J between state P1 prime to state P1. So we get delta P1 minus P2, delta R1 minus R2, delta T1 minus T2, times sum over P1 prime, J P1 prime to P1. Similarly, delta J minus P1 R1 T1, delta J minus P2 R2 T2. I plug again expression for the outgoing fluxes. Delta J of P1 prime R1 T1, delta J P2 prime R2 T2. These guys have the same thing as but 2 instead of 1. And I'm getting sum over P1 prime P2 prime, delta P1 minus P2, delta P1 prime minus P2 prime, delta R1 minus R2, delta T1 minus T2, and the flux that goes from P1 to P1 prime. And this will be equal to delta P1 minus P2, delta R1 minus R2, delta T1 minus T2, sum over P1 prime, J P1 to P1 prime. Okay. Similarly, delta J plus P1 R1 T1, delta J minus P2 R2 T2 will be equal to sum over P1 prime P2 prime, delta J P1 prime P1 R1 T1, delta J here will be an opposite order of indices P2 prime R2 T2, and this will be sum over P1 prime P2 prime, delta P1 prime minus P2, delta P1 minus P2 prime, delta R1 minus R2, delta T1 minus T2, and the flux that flows between state P1 prime to P1. And note that this time both delta functions are getting eaten, and we end up with delta function in space, delta function in time, and the flux that flows between state P2 and P1. And similarly, I would not write the derivation at almost identical, delta J minus P1 R1 T1, delta J plus P2 R2 T2. The same logic will give delta function in space, delta function in time, and the mean flux between state P1 to P2. So now I have correlation function of delta J and delta plus and delta J minus. I can go back and substitute it for the expression and get that the delta J at the point P1 R1 T1, delta J P2 R2 T2, it's equal. All terms have delta function in space. All terms have delta function in time. And then there'll be two terms that will plus plus, and these terms are coming with the plus sign, and they are equal delta J P prime to P plus delta J P to P prime. So these are fluxes, random fluxes that are either coming to or going to the state P from anywhere else, minus J bar between state 1 to P2 and minus J bar P2 to P1. That's the whole thing.
Which P is the P inside of the one with the delta and the momentum?
So this P prime is a dummy variable.
No, yeah, the other P. So is it P1 or P2?
Oh, right. We see this is a delta function.
Ah, right.
So let's choose one. I love one more.
You can have 1 and 2. It doesn't.
You can put 2.
So now we just need to integrate to get rid of the delta.
So this is a limit. So this fully determines the statistics of the Boltzmann noise that stays in the Langevin Boltzmann-Langevin equation. So we managed to convince ourselves that this is the way to postulate the statistics of a Langevin source in the Boltzmann equation. By the way, that this logic goes to the paper by Kogan and Schulman. Sometime in 60s, I guess. Long time ago. If you want to just Google it, it's mentioned in physical kinetics, Lifshitz and Pitayevsky. The papers are not comprehensible, but
the book maybe is.
And the book is not. But I think I've managed to give you. There's another book. There is another book by one of these people. I think by Kogan. It's called electronic. Sorry. No, it's called noise. Sorry, it's called noise in the electronic system. Electronic systems. And I just explained you the main logic of that section. There's nothing more than you need to know. Right. So what we should do that for our problem, if we're talking about non-interacting electrons, acting electrons, no phonons, only disorder. We need to say, okay, so our collision integral will be only collision integral of the disorder type, and the flux of particle that corresponds to the same collision integral between state P to state P prime will be just W P P prime F of P 1 minus F of P prime. And this is the same W that stands in the collision integral. And the entire thing is essentially the incoming part of the collision integral. Collision integral is built of the same blocks as the Lagrange source. And this is actually a very important observation because this procedure needs to be consistent with a fluctuation dissipation theorem. So we know that relation between linear response measurement that are dictated by collision integral, you computed it already many times, and noise must satisfy fluctuation dissipation theorem. Therefore, non-surprisingly, they are built of the same object. So now we're gonna use this knowledge and solve the following problem. Imagine that we have a resistor, normal metallic resistor. This resistor R. This resistor is biased by the voltage source such that the current flows in this system. We know there is a current and it's given by Ohm's law. And we want to compute fluctuations of current in this system. This is our goal. Under external voltage V, and once again, we know that if system is at equilibrium, we know that fluctuation dissipation theorem must hold, and this object, let's call it S2. So this object S2 omega must be equal to conductance times temperature, or temperature divided by resistance. I guess I'm missing factor of 2. This is for omega goes to 0 limit, and more accurate expression is G times H bar omega Katankins hyperbolic of omega over 2 temperatures. So this is the exact quantum mechanical result. And if omega goes to 0, we are going to the classical limit. And this becomes 2 temperature over 2 temperature times conductance. Yeah. In principle, conductance can also be frequency dependent. That's the entire thing. Okay. So that what must happen at equilibrium. And therefore, if you're interested in equilibrium fluctuation, all what you need to do is to measure linear response conductance. And then you know what the fluctuation, the intensity of fluctuation of the current will look like. However, beyond equilibrium, this relation does not hold. And you can ask, what is the fluctuation of current in the resistance, in the resistor, the classical resistance that biased by voltage source, by DC voltage. Surprisingly, quite an interesting problem. Was solved in roughly 20 years ago. Not more recent, that was a source of big controversy and discussions, and a large number published in the high impact factor journals, large number of papers. So even though the problem is very simple. Okay, so how do we solve this problem? Okay, so first of all, of course, we just go back and remind ourselves what is the mean value of the current that flows in this system and how we compute it. And you probably did this exercise already because we were supposed to compute DC current in the Drude equation. And what you did, you took Boltzmann equation and you performed a diffusive approximation and you found that distribution function. So you start with distribution function, which was dependent on momentum, position, and coordinate. Let's think for simplicity about sample, which is quasi one-dimensional. So it means that the sample is long, it has a finite length, and much longer than the length is much longer than its width. Just to then the average part of a distribution function with respect to the momentum, it's called lowest harmonics, and this is this. So there is a part of the function that only depends on the energy, and there is also part of this thing that depends on the direction of the momentum. And typically the first part is much bigger than the second. That's what is called diffusive approximation. And then we could show that the lowest harmonics satisfies the diffusion equation. And the current, electric current density was integral over the energy gradient of this function. And so what we need to do is to solve the diffusive equation with the boundary condition and substitute it into here and to get the current, DC current, and you will get through the formula. I guess I did it at the beginning of our course, but let me remind you that. So let's solve it for the problem when we have a piece of metal. Here will be a chemical potential shifted by applied bias. Here we'll have a chemical potential shifted by applied bias in the opposite direction. So these are called ohmic contacts. And we assume that in the ohmic contact, the distribution function is equilibrium-like. So it will be distribution function with here is this value of chemical potential, and there will be Fermi-Dirac function with that value of chemical potential. So as electron reaches ohmic constant, it has equilibrium distribution function, but the value of chemical potential is shifted because there are bias applied. Then we need to solve this equation in the DC limit, so it means that we can drop the time derivative term. Then we end up with a diffusion equation, very simple diffusion equation that says that the second derivative is equal to 0 and a boundary condition. There's only one function that has second derivative equal to 0, it's a linear function. So we now need to write a linear function that interpolates between these 2 points, and the linear function looks like x over L f of epsilon minus EV over 2 plus 1 minus x over L f of epsilon plus EV over 2. And this is equilibrium function. So if x is equal to 0, we have first term vanish, and we have second term, which means equilibrium function at the chemical potential shifted by voltage over 2. If we're going to the opposite edge of the sample, then we have f of 0 epsilon minus EV over 2. And if we're interested in the current, then current according to this logic will be this guy times integral over d epsilon gradient, which in this case just d over dx, of this object. And you see that the gradient is just 1 over L. Okay, let me write it x over L f0 plus 1 minus x over L f0 Here will be epsilon minus EV over 2. Here will be epsilon plus EV over 2. So this yields E nu divided by L, integral over d epsilon f of epsilon minus EV over 2, equilibrium minus f of epsilon plus EV over 2. This is a Fermi-Dirac function. So this integral yields EV. And therefore we defined a fundamental equation. Sorry, I forgot somewhere. The equation was not just second derivative. Current was the derivative times diffusive, sorry, current was in this formula, and also diffusion coefficient. So diffusion coefficient is here. So I end up with E nu d divided by L times EV. And this was current density. And if I am interested in the total current, I need to take a current density and multiply it by cross section. And therefore I end up with E square nu ds divided by L times voltage. And this quantity, it's called conductance. So I derive the formula E square nu d times S divided by L. And I recovered fundamental Ohm's law. Okay, so that was just a quick reminder of what happens with DC current. And now I need to compute current noise. So how do I do that? Okay, I once again write an expression for current, but this time for fluctuations of the current. And I relate fluctuations of the current to the fluctuations of the distribution function, absolutely analogous to what I did with the mean value. So I integrate with respect to all momentum, the velocity of particles times distribution function, but this time the fluctuation of distribution function. So this is fluctuation in the number of electrons in the state P, R, and T, and these will be fluctuations of current. So that the relation between distribution function and current remains the same. I just replace the expectation value of distribution function with the fluctuation of distribution function. Therefore, the correlation function of currents, let's say component alpha of the current at the point R at time t, component beta of the current at the point R prime t prime, will be now equal to E square integral of this respect to dp with respect to dp prime, V alpha p, V beta p prime, times correlation function of delta f p r and t, delta f of p prime r prime t prime. So I need to compute this object and plug it in, and to compute correlation function of current noise. So how do I compute the correlation function of delta f? I go to the Boltzmann-Langevin equation and I say, okay, delta f satisfies our Boltzmann-Langevin equation. So this is a linear operator. I need to invert this operator. So how do I invert this operator? Let's define a green function for this operator. So what the green function must do? So when you act with this operator on the green function, let's call this green function D, and it be between points PRT and P point P prime R prime T prime, it needs to give you an identity operator, which means delta function with respect to P and P prime, delta function with respect to R and R prime, and delta function with respect to T and T prime. Okay, let's make these delta functions to be continuous delta functions. So if I manage to find this operator, then delta F as a function of P, R, and T will be equal to integral over dP prime, dr prime, dt prime of this green function PRT, P prime, R prime, T prime, delta J external at the point P prime, R prime, T prime. Therefore, the object delta F at P1, R1, T1, delta F at the point P2, R2, and T2 will be just equal to the integral with respect to everything, T1 prime, dr1 prime, dt1 prime, and the same with respect to the second component. Delta P1, R1, T1, P1 prime, R1 prime, T1 prime, delta P2, R2, T2, P2 prime, R2 prime, T2 prime, times delta J external at P1 prime, R1 prime, T1 prime, P2 prime, R2 prime, T2 prime. And okay, so on the level of diffusive approximation, I'll remind you that P, R, and T is essentially f of epsilon P, R, and T. They agree that there is a flux of particles that goes between state P and P prime. And this flux is essentially probability to go from P to P prime times f of epsilon P at the point R at the time T times 1 minus f of epsilon at the energy P at the point R at the time T. Well, since these guys conserve energy, we can just write it as epsilon P. And therefore, the entire correlation function of delta J's, delta J P1, R1, C1, delta J P2, R2, C2, ends up being twice delta function R1 minus R2, delta function T1 minus T2, delta function epsilon P1 minus epsilon P2, because all collisions are elastic. And here I will have minus W between direction of the momentum n1 to the direction of the momentum n2, plus 1 over tau, this will be transport time, delta function n1 minus n2, times distribution function at the energy P1, position R1 times T1, 1 minus F distribution function at the energy P1, R1, T1. And 1 over tau, sorry, this is not 1 over tau transport. I made a mistake. This is just 1 over tau. And 1 over tau, it's just integral over dn, W, n prime. Assuming that the spectrum of electrons is isotropic, and therefore 1 over tau does not depend on 9. Okay, this thing defines everything that I really need. And so I have At this moment, I uniquely define the correlation function of the random fluxes. Therefore, I know my correlation function of random fluxes. Moreover, I know my propagators for Boltzmann equation. So propagator of the Boltzmann equation D between points N1, R1, T1, and points N2, R2, and T2 will now satisfy the Boltzmann equation. So let me just write it explicitly. So it's D over dt1 plus V1 gradient acting on the first component, delta function N1 minus N1 prime, integral with respect, sorry, let me start all over. It would be integral with respect to dn1 prime acting on d over dt1 plus v1 gradient 1 delta function n1 minus n1 prime plus, here comes the collision integral, minus w n1 n1 prime plus delta function n1 minus n1 prime 1 over tau, close the brackets, acting on delta n1 r1 c1 n2 r2 c2. Guess I made a mistake. This should be n1 prime, and all this is equal to delta n1 minus n2 delta r1 minus r2 delta t1 minus t2. So everything is perfectly legit and defined.
Why N1 prime?
Because this is, okay, this integral operator. Now you do some elementary algebra. I did it in my notes. I will not do it here. I just wrote it everything. Just straightforward computation. And the point is that at the end of the day, after you plug it into you plug this equation into equation above, and you get that the correlation function of current delta J alpha at the point 1 symbolically means R1 T1, and correlation function of the current at the point 2. So this is R1 T1, this is R2 T2, is equal to delta alpha beta, delta R1 minus R2, delta T1 minus T2, 2 times sigma integral over d epsilon f of epsilon R1, 1 minus f of epsilon and R1. Here sigma is E square nu d is a conductivity, electric conductivity, T. This delta function comes from the assumption that the spectrum is isotropic. In our model, we use the spectrum, which is epsilon p, being p square over 2m roughly. So this thing is isotropic. This delta function comes from the locality of collisions. This delta function says there is no memory in the problem. And finally, the last in the main building block of this thing is this integral that knows about distribution of electrons inside the sum. So if system is at equilibrium, so let's check at equilibrium. At equilibrium, function f of epsilon and r becomes just r-independent, position-independent Fermi-Dirac function. So if this is the case, we plug that thing into this equation, then the entire thing here becomes temperature. Mhm. Therefore, if you ask what is the integrated current, so that was a current density. Integrated current is the current integrated over area, or 1 over L integrated over volume. Then you get from here that L square di at the time 1, di at the time 2 is equal to delta function T1 minus T2, 2L surface area sigma T. In other words, delta I. Delta I, this is the moment 1, this is the moment 2, will be equal to 2 conductance temperature delta function T1 minus T2, which in the Fourier space delta I in the Fourier will be equal to 2 GT, which is just a classic counterpart of fluctuation dissipation theorem in the omega goes to 0 limit, or omega much smaller than temperature. As it should. However, the whole point of this exercise that now I can say that if system is out of equilibrium, the only thing that I need to do is to replace this distribution function f by actual distribution function of the problem that is away from equilibrium. And we already found this distribution function for non-interacting electrons. We know that this distribution function is actually x over L f of epsilon minus EV over 2 plus L minus x over L f of epsilon plus EV over 2. This is equilibrium Fermi-Dirac functions. So now assume that voltage is much larger than temperature. Then we plug this guy into the expression and we find that integral over with respect to energy f of epsilon nx 1 minus f of epsilon nx is equal to EVx L minus x over L square, which means that if we integrated this thing with respect to dx, this needs to be integrated with respect to dx, we integrate function which is x squared. Okay, so after completing this non-trivial exercise, we get that this is EVA over 6. And therefore, the current correlation function will be equal to 1 over third EG the delta function T1 minus T2. And in the Fourier representation, it will be equal to 1/3 EGV, or in other words, 1/3 E times the mean value of electric current. And this is short noise. And if you compare it with the short noise of a conventional vacuum tube, you see an extra factor of 1/3. So it's universal factor, so to say. For non-interacting electrons, there is a universal factor 1/3 that we got out of nowhere that appears in the disordered piece of metal, which does not exist in the vacuum tube. Lots of papers devoted to this subject 20 years ago. People trying to understand this 1/3 universality. I will explain you probably next time, definitely next time, how you can get this 1/3 from purely quantum mechanical consideration. Notice that here we did everything semi-classically. So people who got it quantum mechanically claim that people who are getting it semi-classically get it totally wrong, and it's just a coincidence. People who derived it semi-classically claim that the people who do it in quantum mechanically do it totally wrong, and that's just a coincidental agreement. In fact, of course, microscopic quantum mechanical computation fully matches semi-classical computation as it should. Both approaches are perfectly legitimate and agree as they should. And it just represents that you can look at the same problem from different perspectives and solve it in different ways. Semi-classical approach has a natural advantage that you can easily add now processes such as, say, electron-electron scattering and solve this problem very fast, as opposed to quantum mechanical treatment that seemingly relies on phase coherence, and therefore it's not even clear how you incorporate electron-electron interaction there. I will give you next home assignment to incorporate, to repeat this problem with the electron-electron interaction. It's not a complicated computation, it's very short, but you will get a different universal answer.
But like, so not 1/3, but something else.
Something else also universal. Square root of 3 over 4, if I remember correctly.
Of what?
Square root of 3 over 4, or maybe square root of 3 over 2.
A very unique number.
Well, if you happen to have a sample and you measure noise in it, and you find a number, then you, by looking at this number, you can tell to what extent
You're in with
you're in this or that regime.
Is this universe number dependent on the dimension?
It's for quasi one-dimensional sample, so it's essentially you take it. It doesn't really depend on the dimension, but if you have a sample, you should be interested in the current which is integrated across the cross section.
Yeah.
So if you have a sample integrated across the cross section, this number is independent of anything, provided that this sample is semi-classical and non-coherent, and we ignore phonons, which makes a difference and make an answer another universal answer. But if you can follow the say voltage and temperature dependence, then by looking at number, you can say what is the ratio between electron-electron lengths, electron-phonon lengths, disorder lengths. So if this thing is longer than elastic length, then there's a universal relation between electron-electron and electron-phonon lengths. That knowing this number, you can see if it agrees or not. So it's a nice exercise for experimentalists. If experimentalists can measure the noise. Okay, you can also play with this approach a bit further and learn how you extract not only second cumulant. So here we discuss second cumulant of current, which was just current. And apparently you can extend these ideas to get any cumulant. This is quite nice. This goes beyond textbook.
They will be all proportional to average.
They will be all proportional to average current. However, the numbers in front of them, the combinatorial coefficients in front of them would be different and universal.
So can I just apply like weak theorem or something, and
it will be
or
okay. If you're interested, I can tell you this. I can tell you how it works. It's not a big theorem, but there's a very funny and physically intuitive way how you explain all cumulants in this problem based on Boltzmann and Given's scheme. However, you need to extend this scheme in a very natural way. You can invent that.
So you, like in the beginning we were talking about Poisson distribution, right?
For Poisson distribution for random scatterings between 2 points in the phase space. So in the individual scattering process between points say P and P prime is indeed Poissonian statistics. But now you need to realize that there are some correlation in the phase space scattering that happened at one point in space. Okay, if you're interested, I can tell you this story. Next time.
So what is the definition again of Poisson process? Yes.
From the textbook of combinatorics, something that has a distribution that we wrote at the beginning a quantity that is
Okay, so there is no like weak theorem for Poisson distribution. It's not Gaussian, right?
it's not Gaussian, no. Poisson distribution is not
Okay.
Gaussian. It has a maximum, so near the maximum it looks like Gaussian.
Like a binary distribution, but the number is near infinity.
Correct. So it's another fundamental distribution, not a Gaussian one. But you can identify, even though elementary processes are Poissonian, you can, if you're really interested, you can find how you can construct all cumulants of currents based on the same philosophy. It's actually doable and very nice. Right. But maybe it's beyond this. Of course, because the problem is that it's very nice, but it's extremely difficult to measure. So experimentalists don't have tools to measure high cumulants of currents. So it remains a purely theoretical story.
Because you like need to measure current at many points.
You need to measure
space and
currents at
time,
many points in time. In many points in time, and cumulants require subtraction of low cumulants. So to get a third cumulant, you need to subtract second cumulant. And because each cumulant gets essentially the central limit theorem works. So central limit theorem says that all distribution functions look like Gaussian. Therefore, all deviations are small, which makes it very hard for experimenters to detect. So when you need to subtract two big quantities to get a tiny difference, it's extremely difficult. So motivation to study these things. No, motivation exists. That would be very useful to measure, but it's just extremely difficult to measure. I spent some time talking to experimentalists who try to do it, and this was very, very difficult. Now, one of the reasons people are interested in this because this short noise is sensitive to the charge of the carrier. Yeah, so if you measure short noise, this is one of the ways to measure what are the fundamental carriers in the system. For example, in quantum Hall, this is how people measure fractional charges by measuring short noise. Now you can go to materials like, I don't know, superconductors, high temperature superconductors, and say, let's measure short noise there. Let's probe the fundamental carriers. What are the fundamental excitations? And then it's very tempting to measure all kinds of cumulants, because that will answer whether you measure, for example, just by coincidence that the fundamental charge is 1/3 of the electron, or there's more to it. Because you can cook one bond, then one theory that has the same fundamental charge. And then if it's a strongly correlated state like quantum Hall, then you will be able to distinguish between different ground state. Yeah, for example, there are some filling fraction where we don't really know what is the fundamental ground state and what are the charges of fundamental excitations. There are more than one candidate. So it would be very nice to see if the picture is consistent and measure this. Extremely difficult to go beyond the second moment. So kind of experiment reached the dead end. But theoretically, it's a very nice exercise. I like it. Anyway, so I guess I'm done explaining this approach. I scan my notes with these technical details in case you want to see how intermediate results are derived. I don't think it makes much sense to derive them in real time because the computations are straightforward, but not
Natural.
not sure. And next time we'll discuss how we get the same results from Landor picture, which is fully quantum mechanical approach. Also a nice chance for you to remind Landor picture. And until the last few lectures of our course, we'll discuss topological materials, how we modify Boltzmann equation to counter the effects of Billy curvature and stuff. And I think that would be more or less the end of it. Okay, so if there are no more questions, let us stop here and see you next time.
Uh,